Hello guys, welcome to Math Side Trips, a channel for math teachers, students, coaches, trainers, and enthusiasts. Thank you for sparing time and effort to visit this channel. Many of the topics that have been discussed and will be discussed in this channel are those that are not usually taken up in mainstream classroom instruction. We hope that you will find in this channel something new, interesting, or useful. This is our channel name, Mathematical Side Trips. In this video, discussion will focus on construction of equations in one variable, in particular, equations involving absolute values. There are three types of equations to consider: A, B, and C. However, we will focus only on type A in this video. The absolute value of ax squared plus bx plus c equals d. The other two types will be taken up in future videos. Arbitrary choices for the constants a, b, and c more often than not lead to solutions which may be real but irrational or complex numbers. This is because after clearing of the absolute value sign, the resulting quadratic equations ax squared plus bx plus c equals d and ax squared plus bx plus c equals negative d may not be factorable. Example, find the solution set of the equation 4x squared minus 3x plus 5 equals 3. Removing the absolute value sign, we have 4x squared minus 3x plus 5 equals 3, or 4x squared minus 3x plus 5 equals negative 3. Each one of which reduces to 4x squared minus 3x plus 2 equals 0, or 4x squared minus 3x plus 8. And from the first equation, we have the discriminant b squared minus 4ac equals negative 23. And from the second, the discriminant is equal to negative 119. Both results indicating that the solutions are irrational complex numbers. So how do we ensure that the constructed equation gives real and rational solutions? Although the constants a and b may be chosen arbitrarily, the constants c and d must be chosen so that the discriminants b squared minus 4a times c minus d is at least 0, and b squared minus 4a times c plus d is also at least 0. And not only that, they must be perfect squares to ensure that the solutions are real and rational. When these conditions are satisfied, the solution set has 4 elements. A very convenient way of construction is by considering any quadratic ax squared plus bx plus c. Then embed any particular value, say x equals k, by letting d equals ak squared plus bk plus c. Then the equation absolute value of ax squared plus bx plus c equals d has at least 2 real and rational solutions. For example, consider the quadratic expression 7x squared minus 13x plus 3 and the particular value x equals 2. Then 7 times 2 squared minus 13 times 2 plus 3 equals 5. And from this we get the equation absolute value of 7x squared minus 13x plus 3 equals 5. And this equation has at least two real rational solutions, namely x equals 2 and x equals negative 1 over 7. Another easy construction is by considering a factorable quadratic expression and writing the constant term as a sum or difference of two other numbers. For example, from the quadratic equation expression 11x squared minus 37x equals negative 28, which is the product of x minus 4 and 11x plus 7, construct an equation of type A. So here the constant term is negative 28, and we rewrite it as negative 35 plus 7, or negative 76 plus 48, or negative 100 plus 72. Then each of the following three equations, absolute value of 11x squared minus 37x plus 7 equals 35, absolute value of 11x squared minus 37 plus 48 equals 76, and absolute value of 11x squared minus 37x plus 72 equals 100, reduces to a pair of quadratic equations, one of which gives the original two real rational solutions, 4 and negative 7 over 11. The following theorem tells us how to choose these constants so that the constructed equation will have 4 real rational solutions. Let ax squared plus bx plus p and ax squared plus bx plus q be two factorable quadratic expressions with rational coefficients and constant terms, where p is greater than q. Then there exist constants c and d such that the equation absolute value of ax squared plus bx plus c equals d has real and rational solutions. Proof: from the quadratic equations ax squared plus bx plus p equals 0 and ax squared plus bx plus q equals 0, we have this equation on the left side. We get this by transposing half of p to the right side of the equation of the equal sign, and then from the second equation we transpose half of q over 2 to the right side of the equal sign, and so these two equations are equivalent to these two. We get the first one by adding q over 2 to both sides of the equation, and the other one we obtain this equation by adding p over 2 to both sides of the equation. And from this we obtain these two equations. It follows that ax squared plus bx plus half of p plus q equals plus or minus p minus q over 2. So we let c be equal to half of p plus q and d equals the absolute value of half p minus q. Clearly, c and d satisfy the requirements. That is, the equation absolute value of ax squared plus bx plus c equals d has 4 real rational solutions. The method as described in the theorem starts with two factorable expressions with the same first two terms, ax squared plus bx. Actually, the method combines the solution sets of the quadratic equations ax squared plus bx plus p equals 0 and ax squared plus bx plus q equals 0. For convenience, p and q may be chosen to be either both even or both odd. Example number 4. Construct an equation of the form absolute value of ax squared plus bx plus c equals d, having 4 real and rational solutions. Consider the quadratic equations 5x squared minus 4x minus 33, which is the product of 5x plus 11 and x minus 3 equals 0. And 5x squared minus 9 equals 5x squared minus 4x minus 9 equals 5x minus 9 times x plus 1, which is also 0. And let c be equal to minus 33 minus 9 equals 2, which is equal to minus 21, and d equals the absolute value of half of minus 33 plus 9 over 2, which is 12. Then from this we get the equation absolute value of 5x squared minus 4x minus 21 equals 12, whose solution set is the set containing the numbers negative 11 over 5, negative 1, 9 over 5, and 3. This is all for now. We hope that you have learned something new, interesting, or useful. Please click the subscription button if you want to subscribe and hit that notification bell for updates about upcoming videos.